professor at PG Department of Mathematics, Berhampur University. Now I am going to present on the topics on the metric space. Metric space is used in many branches of mathematics like the functional analysis, in the operator theory, and in many branches of mathematics it is used. One of the most useful tool for convergence of a sequence of functions as well as the convergence of sequence of operators, and basically it is used in the convergence terms. So we'll define the metric space, some examples, and metric defined on any non-empty set. We'll see different examples. So coming to the next, here some examples. First we will see the definition of the metric space, then examples. We have defined several examples: R, the metric on R, metric on R square, metric on Rn, metric on C to the power n, and also many more examples we have defined. Then we come to the pseudometric space and the algebra of matrices. And a very important part is here we'll see the examples of the not a metric space. We'll see. So then we'll see the definition of the metric space. Let X be a non-empty set here. We'll define metric means it is a map. Function D, which is a mapping from x cross x to R, is said to be a metric or a distance function on x if it satisfies the four properties. D of xy greater than or equal to 0 means non-negative for all xy belongs to x. D of xy is 0 if and only if x is equal to. We are telling this property as a symmetry property. And third one is D of xy is D of yx. And the fourth one is triangle inequality. D of xy less than equal to D of xz plus D of z for all x, y, z belongs to x. A non-empty set together with metric D, we are telling the order pair, is known as the metric space. A non-empty set equipped with the metric, the function D, is known as a metric space. So simply we can write x be a metric space without writing x comma D as the order pair. Now we'll see the example. Coming to the next. Here we have shown the triangle inequality in terms of the figure. You just see that the length of one side of a triangle is greater than or equal to the sum of the length of other two, which is known as the triangle inequality. We have shown in the R2 plane. So we have generalized the triangle inequality if we are taking D of x1, distance between x1 and xn less than equal to D of x1, x2 plus D of x2, x3. We are telling this dot of 2 D of xn minus 1 xn. We are telling this as generalized triangle inequality. So we'll see in the next how to show that. Suppose x is any non-empty set. You have defined a metric on it. We have to check all the four properties whether it is satisfying or not. If the function satisfying these four properties, then we will tell the function as a metric on the specific set x. If one of the properties is violating, if it is not satisfied, then you cannot tell that it is a metric. It may be another definition, maybe a pseudometric. For example, suppose a human being, we are telling about the complete human being. Suppose you are the complete human being, means all the organs, it is right. All the organs are working properly, suppose. If one of the organ is not working, suppose I am telling that your eye is not working, we cannot tell that you are a proper man. You may be called as one-eyed man. We are telling. Similarly, suppose you have one of the leg, suppose you have one of the broken leg. We cannot tell that you are a complete man. Similarly, we have the pseudometric. If the four properties are not satisfied, then we may call it as another name. We'll see in the next. Also, one of the important concepts we are going to discuss, that is known as the induced metric. Before that, I would like to give one of the examples from our day-to-day life. Suppose you are one of the richest men in our state. What about your brother? whether people will call your brother as a rich man or not. It is like that. Suppose the capital X, it has a metric D. Let Y be subset of X. Whether you can define the same metric on Y or not? Yes, you can define the same metric which is defined on X. You can define the same metric on Y. We are telling this metric as induced metric. Here one of the beautiful concepts we have defined. Let X comma D be a metric space. Y be any arbitrary subset of X. Question is, what will be the metric on Y? How to define it? We have defined the metric D or D tilde. We are telling D tilde, which is the restriction metric. D is restricted to Y plus Y. To R. We are telling D tilde as the induced metric, or we are telling it as a relative metric induced, or the metric induced on Y by D. We will see several examples also later on. And Y associated with the induced metric, we are telling it as metric subspace of the metric space X comma D, where XD is our order pair, which is a metric space. Y associated together with the metric D tilde, it is also a metric. So we'll see the next. Here we have defined the examples. The facts are very interesting. Suppose somebody has defined a metric on any set. They have their own defineness. Will we agree that is it a metric? No, not. You have to verify all the four properties. If the four properties are satisfied, then you may call the metric, you may call the function as a metric. Otherwise, no. Suppose you have defined, suppose we are taking the real line R, X be any non-empty set which is denoted as R. R means set of real numbers. Suppose somebody has defined the D of X, distance between X and Y by their own. Whatever may be, maybe X minus Y equal to the power 3, something to the power 1 by 2, suppose they have defined. Will it be a metric or not? If the defined D of XY satisfies all the four properties, then you may call this metric, this function as a metric. Otherwise, no. We'll see beautiful examples of the metric on R. Let X be a non-empty set. We are denoting it as R, set of real numbers. We are equipping the metric D of XY is X minus Y modulus. It is a metric on R. It is very trivial to check whether it satisfies four properties or not. Since modulus is there, you can tell that it is greater than or equal to 0. Suppose D of XY is equal to 0, if and only if X is equal to Y, we have to check. D of XY means X minus Y modulus is equal to 0. You can imply that X is equal to Y. If X is equal to Y, also you may call that D of XY is equal to 0. Both are satisfied. The triangle inequality also it is coming. By the dependence of X minus Y modulus, we know that the mod X has two values. Mod X is X when X is greater than or equal to 0. Is minus X when X is less than. By using the dependence of X minus Y modulus, you can use the triangle inequality. Also easiest one. So similarly, we are showing here X comma D, R comma D is a metric space with respect to this definance X minus Y modulus. Question arises here, whether you can define the other metric on R or not. Answer is yes, affirmative. You may get several matrices on this same set R. We'll see other examples. These examples are very beautiful, and also we have collected many data from different sources. We have shown that yes, it is a metric on R. Really good thing we have done. D of X, you just see that another metric we have defined on the same set X is equal to R. D of XY is X minus Y modulus plus 1. If exactly one among X and Y is strictly positive, and X minus Y modulus otherwise, it is also a metric on R. You can easily check whether it is a metric or not. Similarly, one more metric also defined on R, that is and x minus y modulus plus 1 if exactly 1 among y. Here it is strictly positive, and the last one also it is strictly positive. For all x y it belongs to R. I think it is been repeated. So we will come to the next. Here it is, we have defined d of xy is tan inverse x minus tan inverse y modulus R. Tan means tan inverse x minus tan inverse. This type of questions are coming in many competitive examinations like CSIR, NET and GATE examinations. So have you collected all the matrices on R or not? Really it is a beautiful question. Whether can you define several matrices on a same set R or not? If you have recalled, if you have remembered, if you have collected all the data, all the matrices on R, really you can defend almost all the questions, competitive examination questions in mathematics. Really we have a good collection here. D of xy is tan inverse x minus tan inverse y modulus. It is also a metric on R. You can easily verify whether it is greater than equal to 0, whether it is 0 if and only if x equal to y or not. Little bit work is required. And coming to the next example, also on the same R, d of xy is logarithmic of 1 plus x minus y modulus. The R equipped with the same metric D is known as the metric space. The next is we have defined d of xy is log of y by x modulus. It is also a metric on R. You can easily check it. Coming to the most beautiful property. Okay, we will discuss in the next that how it is coming. I have written d of xy is minimum of d comma 1. Where d we have defined the usual metric x minus y modulus. One of the property also we will discuss here, the algebra of matrices. If d is a metric, d1 is a metric on x, d2 is a metric on x. What about d1 plus d2? What about d1 maximum of d1 d2? What about minimum of d1 d2? Will it be a metric or not? Yes, this concept compelled us to think about the d of xy is minimum of d comma 1. It is also a metric. You can define. You just see that one of the concept is there in real analysis, how to define the minimum function, minimum of x and y. Similarly, maximum of x and y. Once you are defining the minimum of x and y, by using the dependence, you can check whether it is satisfying 4 properties or not. Once it is satisfying all the 4 properties, you may call it as metric. Here also we have written, slowly we are coming to the difficulty. Here we do not have any restriction on R. We are taking x as any, x is the real number set of all real numbers. The next example we have a restriction. Here you can take d of xy is modulus of e to the power x minus e to the power y. Where for all xy belongs to R, it is the non-empty set x means R equipped to the symmetry D is known as the metric space. Here we have taken another example as R minus the singleton set. We have excluded 0. We can define the d of xy is 1 by x minus 1 by y modulus. One of the beautiful questions on the metric on R. Really, we have a good collection. We have defined several matrices on the same set R here. So you can collect also another example, the same metric or the different matrices on R also. I mean to tell that if X is any non-empty set, my question is, can you equip a single metric or more than one metric? Answer is affirmative. Yes, you can equip, you can adjoin, you can join more than one matrices on a single set X. One of the, in my sense, one of the beautiful concepts. Suppose I am telling the notion of the metric means the distance function. We are telling the distance. Suppose you are here, you want to reach at Puri. In how many ways you can reach? You can reach to Puri by using road. by using rain, by using air, by using your vehicle, by using the water, in the path of the water, you can use the path. So in many ways you can reach from one point to another. Similarly, here we are defining several matrices to find the distance between x and y. That's why we are collecting the different matrices on R. Here, coming to the extended real number line, means in R we do not have infinity and minus infinity. We have the open interval minus infinity set up for real numbers lies between minus infinity to plus infinity, not including minus infinity and infinity. If you will include minus infinity and infinity, what will the corresponding metric you can define on the extended real number system or extended real number line? We are telling R as line. If we are adding infinity and minus infinity to R, we are telling it as we are telling it this as extended real number system. Then question arises, what is the metric on R has? We are denoting sometimes it as R has. Here, if you are taking x equal to R, union the singleton set infinity, union minus singleton set infinity, then you can define the metric. Here, f of x means metric. You can define f of x as x by 1 plus mod x if x lies between minus infinity and infinity. If x is infinity, it has the value 1. If x is minus infinity, it has the value minus 1. Here we can check the kernel of f is kernel of f means collection of x where f of x is 0. We are telling it as it is a subset of the domain of f. It is easy to check that kernel of f is singleton set 0. So we are telling that f is 1 to 1. Another way to check 1 to 1. Also, you have known f is set to be 1, 1, 1. If you are using one of the trivial problems, if f of x is equal to f of y, if you can imply that x is equal to y, you can tell that f is 1, 1. Here we have shown in the another way, if kernel of f is equal to singleton set 0 implies f is 1. This property is frequently used in the functional analysis. Okay. So here say f is 1, 1 and f of x, the range of f of x. The f of x lies between minus 1 to 1. So we are defining the metric d on x as d of xy is f of x minus f of y modulus. For all xy belongs to x, x means the extended real number system. It is also a metric on the extended real number system. That means we are defining the metric in terms of the function. So one of the critical definitions of the metric on R has. So we will come to the next. Coming to the induced matrices on subsets of R. Here we have taken Q as the subset of R. Q is the set of all rational numbers. You can define the d of xy, which is x minus y modulus. It is also the metric on R. We are telling the d of xy, which is defined as x minus y modulus, as the induced metric on the subset of R, which is known as Q. We are telling x comma d is a metric space where x is in Q. Similarly, if you consider another subset of R, which is Z, question arises which metric, Z means set of all integers. Question arises which metric you will equip on x so that you can form the metric space, the order pair x comma d. Yes, we can define the same metric which was defined on R. We are telling it as the induced metric. Similarly, if we take x as non-empty set, let x be n, set of all natural numbers. We can define d of xy is 1 by x minus 1 by y modulus, which is also a metric on n. If we take the closed interval 0 and open 1, semi-open interval, we can define the same metric which was defined as an R. D of xy is x minus y modulus. It is also a metric on 0 closed, 1 open. Similarly, we can define another metric on the same set, the semi-open interval. D of xy is 1 by x minus 1 by y modulus, it is also a metric on R. If we take any open interval which is subset of R, also we will have the same metric on the open interval AB. We are telling this metric as the induced metric. Why it is induced? Because we had defined the metric on R. It is also used on any subset of R. That's why we are telling it as induced metric. So we'll come to the next. Here we are taking as the another example as R square, which is R plus R. We are telling this as Euclidean plane. This is a set consisting of all ordered pairs xy or x1 y1, where x1 y1 are the elements of R. How to define a metric on R square? Gradually we'll see whether we'll be capable to define the metric on any non-empty set or not. How to define the distance between any two non-empty sets? Really a quite interesting question. Here we are imposing how to define the distance between any two elements on any non-empty set X. That's why the concept metric is quite interesting to define the notion of the distance between 2 points of any non-empty set. So here we are taking R square. Similarly, we will take R cube. Similarly, we will take Rn. We may consider C or C square, Cn. We may take any non-empty set. Slowly, gradually, we will consider different non-empty set. We will see how we are equipping the metric on the non-empty set X. We are taking R square, d of xy. We are defining d2, the equivalent metric d2 of xy, where x is x1, y1 and y is y1, y2, because we will take the order pairs as the elements of R square. So how to define the metric on d2 of xy is the distance between x and y, which is square root of x1 minus y1 whole square plus x2 minus y2 whole square. We are telling d2, the non-empty set X means R square associated with the metric d2 is a metric space. You can easily verify whether it is a metric or not. You have to check the four properties: d of xy greater than equal to 0, d of xy is equal to 0 if and only if x equal to y, d of xy is it d of yx or not, and last one is the triangle equivalent. Since it is satisfying all the four properties, so we are telling this as a metric on R square. Similarly, one more metric we can define on R square. We are telling it as a dp metric. For any p lies between 1 to infinity, excluding infinity. Here we are defining the dp of xy is x1 minus y1 modulus to the power p plus x2 minus y2 modulus to the power p whole to the power 1 by p. P lies between 1 to infinity, including 1. Also we will discuss what about the infinity metric. It will be the maximum of both the terms x1 minus y1 modulus and x2 minus y2 modulus. So in general you can tell that x associated with the dp metric is known as a metric space. We have generalized here. For any value of p, if we take p as 3 by 2, what will be the d3 by 2 metric? You can define any metric. You just see that how many matrices you can define on R square. Is it finite or infinite number of matrices you can generate? Answer is infinite number of matrices you can generate on R square. Any metric you can define on R square. So not that it is restricted to one only. Similarly, another possible metric on R square is d of xy is x1 minus y1 modulus if x2 is same as y2. Otherwise, it has the value x1 modulus plus x2 minus y2 modulus plus y1 modulus. The d of xy, the non-empty set x together with means R square, together with this definition of the metric d, we are telling it as a metric space. Coming to the next, we'll see. You just see that gradually we are increasing the dimension of R. Rn. In the beginning example, in the beginning we had discussed about R. Gradually we took R square. Next we took Rn. Then you may discuss about the C square, Cn. This type of examples we can consider. If we consider another example like set of all functions, continuous functions, the matter will be different. The definition of the metric will be different. Here we see the Rn, means R cross n copies of R. The elements of Rn are the n tuple vectors, x1, x2, xn out of n, where all xi belongs to R. You can define the 2 metric. Slowly we are considering, we are dealing as Euclidean metric. The distance, all of you have known, all of you have the idea about the distance between 2 points on R square. Similarly, we are extending this idea to Rn, means x1 minus y1 whole square plus x2 minus y2 whole square plus dot xn minus yn whole square whole to the power 1 by 2. We are telling it as a D2 metric. The question arises, why you are denoting it as D2? Why not D1? Yes, we can denote it as D1. It will have the another defineness. In the next example, we are considering here the DP metric, where P includes also 1. P lies between 1 to infinity. Here we have defined also the D infinity metric. In DP of xy, you will be astonished to know that you can generate infinitely many matrices on Rn. Quite interesting example we have introduced here. The DP of xy, which is summation of xi minus yi modulus whole to the power p whole to the power 1 by p. P lies between 1 to infinity. And similarly, d infinity of xy we are defining as maximum of xi minus yi modulus. I lies between 1 to infinity. The non-empty set X together with the DP metric, or non-empty set X together with the D infinity metric, we are telling this as the metric spaces. One, this is also a metric space, another one is also the metric space. Coming to the next example, if we consider C, I was telling earlier about the complex plane C, set up all complex numbers. Z is equal to x plus I, we are considering the complex number as Z, where x and y are real numbers. If we take x is equal to C, the question arises, what will the metric on it? The D of Z1, we are considering Z1, Z2 are the complex numbers, not we are considering here the x and y. X and y, we are taking as the numbers for Rn, for Cn. These are the elements we are considering. Here we are considering Z1, Z2. The distance from Z1 and distance between Z1 and Z2 defined by Z1 modulus plus Z2 modulus if Z1 not equal to Z2, and if it has the value 0 otherwise. This will define a metric on x is equal to C. Similarly, if we extend the idea to Cn, quite interesting one, we are telling Cn as unitary space. Cn means C cross C cross C, n copies of C. The elements of a Cn are the n tuple vectors of a C. Each elements are the elements of a C. So we are considering Z1, Z2, Zn, n tuple vector. Each entries are the elements of a C. Similarly, W will be another element, W1, W2, Wn. These are elements of a Cn. The question is, what is the distance between Z and W? You can define the DP metric. Here we have generalized all the things. We have not defined here 1 metric, 2 metric, 3 metric, or 3 by 2 metric, or we have not discussed. In general, we have written the DP metric. You just see that what in my sense it is a beautiful collection regarding the metric on Rn, Cn, and also many more examples we are considering here. The D infinity metric is maximum of the modulus of this, which is also a metric on Cn. Coming to the next example. Yes. one of the beautiful metric on any non-empty set. You just see that suppose you don't know about the nature of the elements of X. X may be any set. Here, any blind fellow, blind, can define the discrete metric. At least this set means it has some elements. So if the two elements are not same, it has the distance 1. If these are same, it has the value 0. D of xy is 0 if x is equal to 1. D of xy is 1 if x is not equal to 1. What is x? The small x and small y are the elements of x. What about the capital X? Capital X may be any non-empty set. We do not have any restriction here. So one of the metric, blindly you can define the discrete metric on any set. Suppose you are not able to define a metric on any non-empty set. Define a discrete metric. It's easy to define. Also you can easily check whether it is a metric or not, whether it satisfies all the 4 properties or not. Definitely d of xy is 1, since it is 1 it is greater than equal to 0. And d of xy is d of yx because it has the value 0 and 1. D of xy less than equal to d of xz plus d of zy. You can easily check the triangle inequality and all the 4 properties. So it will be metric on any non-empty set X. Coming to the another type of distance, since we are considering the distance function, here we are discussing the Hamming distance. Let X be the set of all ordered tuples of zeros and ones. We are considering the elements of the order pair where the entries are zeros and ones. So here X, we are taking X consists of 8 elements. The order pair 8 elements. Where d of xy is number of places where x and y have different entries. If you are defining the metric like this, then also it will form a metric space. We are telling this distance as Hamming distance between x and y. Quite interesting one. And the non-empty set together with the Hamming distance, we are also telling it as a metric space. Here another distance we have defined here for any non-empty set A. Let X denote the family of all finite subsets of A. We are not telling that we may not tell that it is a power set, but we are considering that X is the family of all finite. We have considered that finite subsets of A. Let X delta Y denote the symmetric difference between two subsets X and Y of A. We are defining the metric d of xy is hash of x delta y, the number of elements in x delta y. It is the meaning. The non-empty set X together with the metric D is also a metric space. Coming to the metric on the sequence space, here LP we are considering set of all sequences Xn in R or C. We are taking it as real or complex sequence. Where the terms are pth summable. Summation of xi modulus to the p is convergent. In that space, in that set, how to define a metric on it? The question arises whether you will be able to define the metric, the distance between any two elements from LP, where elements are the sequences. Really, I am being astonished that we are able to define the distance between two sequences. How to define the element? You just say, suppose Xn is a sequence. Means it has elements x1, x2, x3, dot dot dot. Yn is another sequence. Y1, Y2, Y. The term, I am telling you the terms of the sequence. Y1, Y2, Y3, Yn. So how to define the distance between Xn and Yn? In terms of the terms of the sequences. So here we have defined the dp metric. Directly we have written the DP metric, you can consider P as 1, 2, 3, or you can consider, not that we are taking P as only the natural numbers. You can take any real numbers lies between 1 to infinity. You can consider P as 3 by 2. Here we are defining the DP metric on LP as dP of xy is summation of I is 1 to infinity xi minus yi modulus to the p whole to the power 1 by p, where x and y are the elements of the LP. LP means the sequences. The x and y are the sequences from LP, real valued or complex valued sequences. So the non-empty set, the LP together with the metric DP is known as the metric space. You can easily, of course, to define or to prove the triangle inequality, some auxiliary inequalities are required. For example, the Minkowski inequality is used here to show the triangle inequality. And also sometimes we can use the Holder's inequality to show the triangle. So some auxiliary inequalities will be used to show the triangle inequality, because here the summation is not the finite summation, it is an infinite summation. So some auxiliary inequalities are required. It has already been done, not that it is research work. So the proof is available in any of the textbooks of functional analysis. So x associated with the DP is a metric space. I will come to the next example. Here, very important part is we have restricted the value of p to 0 to 1. Whether can we able to define the metric on the LP space, the same LP, the set of all elements, the sequences, where the terms are the real or complex numbers, real valued or complex valued sequences, but the restriction is p lies between 0 to 1. In that case, we are defining the DP star. We are not writing the same metric DP, because DP we have already defined in the LP, where the range of p lies between lies between 1 to infinity. Here we are considering the range of p as 0 to 1. You can define the DP star of xy is summation of I is equal to 1 to infinity xi minus yi modulus to the p, where p lies between 0 to 1, and x and y are the elements of the same set LP. Here the restriction is p lies between 0 to 1. It is also a metric on the space on the set LP, the non-empty set, together with the metric is known as also a metric space. We will consider the L infinity, set of all bounded sequences. The xn, collection of these sequences where xn modulus is less than finite, is some positive real number here. We are telling as sequence is said to be bounded if there is a real number, positive real number here, so that xn modulus is less than equal to here. So collection of all bounded sequences. How to define a metric on it? We are writing it as L infinity. We are defining the D infinity metric, the supremum of xi minus y. Xi and yi are the terms of the sequence x and y, where x and y are the elements of L in sequence. The non-empty set L infinity associated with the D infinity metric, we are dealing as a metric space. Here we are defining metric, many matrices on any non-empty set. Then whether we can construct the metric space or not? Yes, it is obvious. So coming to the next example, you just see that one thing I want to tell here. In the beginning of the example, we had considered R. Then we came to Rn, then C, then Cn. In Cn, we are considering the n tuple vectors. N, the number of elements in the n tuple vector are n. Slowly, we are considering the LP, the same form. The sequence xn, we are considering xn, the order pair, which has infinitely many elements x1, x2, xn. So why we are considering in this why we are considering the examples of the metric in this sequence? Gradually we are observing the dependence of the elements of the set. That's why we have noted here. We have set the elements, the examples of metric space from R, Rn, C, Cn, then Lp. It has a good sequence in my sense. So, okay, we'll consider the next set. Let X be any set of all real sequences. Here the elements are the sequences. There is a restriction. Let X is equal to Xn the sequence and greater than or equal to 1. Y with the Yn where n greater than or equal to 1 be arbitrary elements in X. We are defining here the distance. Really interesting one. 1 by summation of 1 by I square minimum of xi minus yi and 1. This summation is infinite summation. The non-empty set X together with this dependence of the metric. The metric is known as also a metric space. Here you just see that we have not included here the proof, all the proofs. A little challenging one. Sometimes the triangle inequality may put you in the trouble, but all the rest properties, you will try your best, it will be easy to prove the rest 3 properties. Another example here we are considering, let X be the set of a real sequence. So we will take Xn and Yn are 2 sequences, are 2 points to be close to each other if their first n terms are equal for some large first n terms, if the first n terms are equal for some large, then we can define the d of xy is 0 if x equal to y, and d of xy is 1 by minimum of I, where the xi and yi are not same. I am talking about that index I. If x not equal to y, the non-empty set together with this metric is known as a metric space. So we will come to the next example. Not that the elements are like the tuple vectors. Rn not like the elements of Rn, Cn, Lp, L infinity, and like the elements where in the order form. Here we are considering the different types of a set where the elements are the functions. CAB, the set of all real valued continuous functions defined at the closed interval AB. How to define a metric or distance between any 2 functions here. We are considering X and Y are 2 functions, not 2 real numbers. 2 real valued or complex valued functions, 2 scalar valued functions. The interesting fact is, here we have defined the d1 of x. I will tell you why we have written d1. d1 of xy is integration from a to b x of t minus y of t modulus dt. If we write d2 of xy, will you tell that what will be the corresponding metric for CAB? d2 of xy. Definitely one can guess d2 of xy will be integration from a to b modulus of x of t minus y of t whole square whole to the power 1 by 2. Similarly, you can define the dp metric. Gradually you have written here, perhaps in the next. So in the CAB we are defining only one metric. It is possible to define the infinitely many matrices on CAB. It is also a metric you can easily check. Triangle inequality is also easy to check, and all the 3 properties are being satisfied. We will come to the next example. Let X be any non-empty set of all real or complex valued defined and bounded on A. It is a bounded function. The metric defined on B of A is defined by d infinity of xy, the supremum of x of t minus y of t modulus, where t belongs A means A is a set. the sup denotes the supremum. We are telling it is called the uniform metric, and the set is called the space of bounded function. The non-empty set X together with the D-infinite metric is known as also a metric space. So we will come to the next example. Yes, I was discussing about the complete men and incomplete men. Here we are discussing about the pseudo-metric space. The metric where one of the property will not hold good here. Let X may be any non-empty set. It is definition of the pseudo-metric is exactly like the metric space except one property. A function D from mapping from X cross X to R is said to be a pseudo-metric if it satisfies the four properties. Also we have here four properties. D of xy greater than equal to 0 for all xy belongs to X. D of xy is 0 if X is equal to Y. The rest part is absent here. In the second point, in the metric space, we had D of xy is 0 if and only if X is equal to Y. Here one of the property is absent. Only the part is if X is equal to Y, we are taking D of xy is 0 and D of xy is D of yx and the triangle inequality. All the properties are same like the metric space except the second one. Second one of the property we have left. The non-empty set together with this metric which satisfies these four properties is known as a pseudo-metric space, or we are telling it as a pseudo-metric. We have one the remark. Every metric space is a pseudo-metric space, but the converse is not true. Beautiful examples are also here. Now we come to the next examples of the pseudo-metric space. Let X may be any non-empty set. We are defining D of xy is 0 for all xy belongs to X. It is also a pseudo-metric or trivial metric. Very important example is the third one. It is quite interesting. If you consider X is equal to R, this set of real numbers, if you are defining D of xy is sin of x minus y modulus. So since modulus is there, D of xy greater than equal to 0. We will consider the second one. Suppose X is equal to y. Will you imply that D of xy is equal to 0? Yes, it is obvious. If X is equal to y, D of xy is sin of 0. Means sin of 0 is 0. Modulus is there, so it is 0. We will consider the reverse one. Suppose D of xy is equal to 0. What you will get? You will get modulus of sin x minus y will be 0. Mod x is 0 means x is equal to 0. Means sin of x minus y is equal to 0. If sin of x minus y is 0, will you imply that x minus y is equal to 0 or other than the 0? If sin of x minus y is 0, you may imply that x minus y is n pi. So x is equal to y plus n pi. X may not be same as y. X is different from y. So here one of the properties is violated, so we are considering the best example. It is a pseudo-metric. Also the second one is also a pseudo-metric. D of xy is x square minus y square. Suppose x is equal to y. You can imply that D of xy is equal to 0. Suppose D of xy is equal to 0. That means x square minus y square is equal to 0. You are getting x is equal to y and x is equal to minus y. X square minus y square means x plus y into x minus y is 0. So you are getting x is equal to y in one of these sense. In other sense you are getting x is equal to minus y. You cannot imply that x is exactly equal to y. Another form also you are getting. So we are considering the fourth example as set of all Riemann integrable functions on the closed interval AB. If you will define D of fg, where f and g are Riemann integrable functions on the closed interval AB, then D of fg is integration from a to b f of x minus g of x modulus dx. It is also a pseudo-metric which is not a metric. So we will come to the next example. Coming to the algebra of matrices, I was discussing earlier that if D1 is a metric on X, D2 be another metric. What about D1 plus D2? What about D1 into D2? What about minimum of D1 and D2? Maximum of D1 D2? We are telling here we are in a position to discuss about the algebra of matrices. Quite interesting property. Let x comma d be a metric space for all x y belongs to x. If you are defining d tilde of x y, another metric is k into d of x y, where k greater than 0. Here important part is we are multiplying a non-negative number, real number. It will also be a metric on R on any non-empty set x. Similarly, square root of d of xy. If d of xy is a metric on x, what will the square root of d of d? Square root of d. Will it form a metric? Yes. Answer is yes. It will be a metric on. You can easily verify the 4 properties. Coming to the maximum of d1 d2. If d1 and d2 are 2 matrices on the any non-empty set x, the maximum of d1 d2. I was telling that the maximum is a function. You can define maximum of d1 d2 as d1 plus d2 plus modulus of d1 minus d2 divided by 2. It has a definedness. So according to the definedness, you can prove whether it will be a metric or not. You have to satisfy all the 4 properties. Similarly, minimum of 1 and d, whether it will form a metric or not. We were discussing earlier. Here coming to the next algebra of matrices, if you are taking d1 plus d2 as another metric, whether it will satisfy the 4 properties or yes, answer is affirmative. We are getting another metric on any non-empty set x. So coming to the next property of the algebra, one of the beautiful algebraic property. Here I am just recalling about the translation invariance property. We are not discussing here about the non-linear space. It plays an important role in the non-linear space. I am telling about the metric which is obtained from the norm. The metric which satisfies the translation invariance properties. These matrices are obtained from the norm. One of the best definers of the metric is this type of metric is not obtained from any norm because it will not satisfy the translation invariance property. Okay, we will not go to that part. If we are defining here d by 1 plus d. D is a metric on any non-empty set x. How to generate another metric with the help of d? I was telling that minimum of 1 and d will be also a metric. Maximum of d1 d2 is a metric. d1 plus d2 is a metric. We are discussing here the algebra of matrices. Similarly, d by 1 plus d is also a metric on the same set x. Here, the product matrix space. Slowly, we are going to the depth of the concept. Not that we are considering x as any non-empty set. If we will take x as the product of 2 sets, x1 and x2 be 2 non-empty sets. If we are taking the Cartesian product of 2 sets, we know about the Cartesian product of 2 sets. Then how to define the metric on the Cartesian product of 2 sets? Already we have discussed the examples. R cross R. Here we are considering the generalization. Not that R cross R. We are taking x cross x1 cross x2, where x1 and x2 are any 2 non-empty sets. Here x1 associated with the d1 is a metric space. x2 associated with the d2 is also another metric space. Question is how to define a metric on x1 cross x2. Here we are defining here the d tilde of xy is d1 plus d2. Is also a metric on the product metric space. Another metric also you can define the d1 square plus d2 square to the power 1 by 2. And maximum of d1 d2, it will also give you another metric on the product space x1 x2. The product space x1 x2 together with these matrices we are telling it as a metric space. We are considering here the product metric space. So coming to the next example, here suppose you are taking d1 d2 two metric on X, whether d1 square plus d2 square to the power 1 by 2, will it form a metric or not? Yes, it will form a metric. We are considering here the algebra of matrices, really quite interesting one. We have devoted much more of a time to collect all the matrices and the algebra of matrices and the material available, the literature available on the regarding the metric. So one of the best properties d1 square plus d2 square to the power 1 by 2 is also a metric on any non-empty set X, where d1 and d2 are the metric on X. Similarly, if we take union of, you just observe that we are considering different types of sets, whether we will be able to define the metric on the set X or not. Yes, if we will cover all the theories, then you can define a metric on any non-empty set. We considered Rn, Cn, Lp, Cab, L infinity. Also you can define the metric on capital Lp, which we are telling it as Lebesgue space, space of all pth Lebesgue integrable measurable functions. So here we are taking union of two sets, whether you can define a metric or not. Let X comma D be a metric space, X1 and X2 be two disjoint non-empty subsets of X, where X is the X1 union X2. You can define d tilde of xy is d of xy plus 1 when exactly one among x and y belongs to x1, and d of xy and you can define d of xy otherwise. With this defineness, the union of two sets with the d tilde will form a metric. Here I was telling about the minimum of 1 and 3. It will also form a metric. You can define the minimum for two functions, two elements as x plus y. Suppose x and y are two elements. How to define minimum of x and y? X plus y minus modulus of x minus y divided by 2. If we take x, you just see that in case of complex numbers you cannot define the minimum of two numbers or maximum of two numbers. We are considering the minimum and maximum for real numbers and real valued functions. You cannot consider the same thing in case of complex valued functions and complex numbers. It is not possible. So you can define the minimum of this by using the defineness. You can do the proof of all four properties, and the non-empty set together with this metric is known as also a metric space. So we'll see the next example. Yes, examples of not a metric space. Here you just see that we have collected many examples on the same set R, where it will satisfy, it will not satisfy all the four properties. It may satisfy two properties and rest properties are violating here. You just see that d of xy is x square minus y square. Can you tell which property will be violated here? If x and y are real numbers, suppose we will consider d of xy is greater than or equal to 0 or not. We will check. It may not. Suppose d of x and y are real numbers. We have not taken here the modulus. D of xy is x square minus y square. It may not. It will not satisfy. The d of xy is greater than or equal to 0. Once it is not satisfying at least one of the property from the metric, so it will not be a metric space. The non-empty set together with this metric is not a metric space. Question is, suppose you are, I was telling earlier, suppose you are defining a metric on any non-empty set by your own choice. Not that it will be a metric. It should satisfy all four properties. D of xy greater than or equal to 0. D of xy is equal to 0 if and only if x is equal to y. And d of xy is d of yx and the triangle in it. D of xy less than or d of xz plus d of xzy. For all x, y, z belongs to the capital X. If the metric, the distance function D, if it is satisfy all the four properties, the non-empty set together with the distance function, we are telling it as a metric space. So I am not coming about the more examples on not a metric. You just see that plenty of examples we have collected here. On the same set R, we have the restriction. You just see that x is equal to y. What I am recalling, one of the example in our four examples. This type of questions are coming in the CSR examinations. Suppose they are giving let x is equal to R. They have written several matrices on R. Which of the following will be a metric on R? They are asking. If you are truly acquainted with the several definitions of the metric on R, you can judge. You may be knowing about which of the option will be true. This is a good collection regarding the metric space on any non-empty set. So I am coming to the next example of not a metric space. Here we have defined the x is equal to Cn. The dp metric, here the restriction is p lies between 0 to 1. If you are defining the dp metric, it will not form a metric. The range of p is very important. If you take range of p as 1 to infinity, it will form a metric. But if you are taking the range of p as 0 to 1, open interval, if p belongs to the open interval 0 1, then it will not form a metric on Cn. Similarly, we are taking set of Riemann integral functions on the closed interval AB. Here we are defining the one metric. What we are recalling here, it is one metric. It is not a metric on the set X. Similarly, one of the property from our algebra, we had considered here, if D1 is a metric on X, D2 is a metric on X, whether D1 plus D2 is it a metric? Yes. What about D1 minus D2? May not be a metric, because D1 minus D2 may not be greater than equal to 0, may be negative. So at least one of the properties is violating here. So D1 minus D2 is not a metric on any non-empty set X, where D1 and D2 are the matrices of X. So with this we will wind up the discussion on the metric on any non-empty set. You just see that the quite interesting facts are here. I will raise only two questions. Suppose X is any non-empty set here. Will you be able to define a metric on it? Answer is yes. At least you have the discrete metric. Another question is, how many matrices you can generate? How many matrices you can equip on a non-empty set? Infinitely many. Not that if X is any non-empty set, not that a single metric is possible only for this set. You can also define another metric. You may ask the question, sir, how? You just see that suppose X has only one metric. You just see that how I am generating another metric. By using the algebra of matrices. Minimum of 1 and D, it will form another metric. And D by 1 plus D, it is also another metric. So at least discrete metric you have, you can define D of xy is 0 when x is equal to y, D of xy is 1 when x is not equal to. So I mean to tell that on a non-empty set X, you can define at least more than one matrices on X. So with this we'll wind up the discussion on the topics of the metric space. So coming to another example of the algebra of matrices, you just see that we were considering if D1 is a metric on X, D2 is a metric on X, so that D1 into D2, will it form a metric on X? Answer is no. Answer, we are getting the negative answer here. If D1 into D2, you are given a D tilde, it will not form a metric on X. Similarly, we had considered in the previous example that a minimum of 1 and D will form a metric on X. but minimum of D1 and D2, it may not form a metric on the set X. So with this, we'll conclude all the examples. You just see that we have discussed the examples, the definitions, examples of not a metric space and good collection of matrices and algebra of matrices. With this, we'll wind up the discussion on metric space. So, thank you all.